Our next topic in this little mini mole session is going to be molarity. When we're talking about molarity, we're discussing a solution. Now, solutions are considered to be aqueous unless otherwise specified. And what that means is that water is our solvent. You saw this last year. This should be a quick review for you. We use a capital M. It's moles of solute per liters of, now notice this, solution. Be very careful because molality differs. Now remember I mentioned earlier that a convenient substitution for moles is to write mass over molar mass. And I find I use this formula as much as I use this one. And you can look those up on your formula chart, but that just takes time. You might want to memorize them. Now, a few comments about molarity before we calculate the molarity of a substance. The first is to realize that molarity is an intensive property. Just like if I had 10 mLs of water, if I'm at a certain temperature just above 3 degrees, its density is 1 gram per ml. Well, if I have 1 milliliter of water, my density is still 1 gram per ml. Intensive means it's independent of the amount of solution or substance that you have. This is true for molarity. So if in the lab you go see a bottle that has a big 6 capital M, which we would say is 6 molar solution, just a little shortening of that word, if you pour out of that 50 mLs from that big bottle, it's still a 6 molar solution. So we call this a homogeneous mixture. So it's a measurement of a solution. To make these, and you will get an opportunity to do this in AP chemistry, we're going to use a volumetric flask. Now, a volumetric flask does not have many lines on it. In fact, it has a single line. But don't let that fool you. Our volumetric flask, along with our milligram balance, are our two best pieces of equipment in our lab that we have available to us at the high school. So it only does one volume, but it does it very, very, very well. And we'll talk about how to make a solution in just a moment. So we'll use a volumetric flask. Now we're going to need to know this in just a little while. Molarity, again, since it is an intensive property, we're going to be able to assume any amount that we need. And this is going to be particularly important when we're doing conversions between molarity and molality and percent by mass. We're going to cover each and every one of these, and mole fraction. And there's certainly more. We could be talking about percent by volume, and we could be talking about parts per million, parts per trillion, parts per billion. I'm going to save those for another day. AP chemistry doesn't focus on those right now, as important as they are in some industries. We just have to kind of draw a line in the sand of what we need to learn at this level. And so we're going to focus on these. And you need to know that these are all intensive properties if we want to interconvert among them. Now, molarity can also be used as a conversion factor. We'll discuss that more in Chapter 3 on stoichiometry. But whenever you have a double unit, grams per mole, for example, we saw earlier that ammonia was 17.04 grams per mole, we can write any double unit like that as grams equal to 1 mole. And when you have that equality, you have a conversion factor that we can use in a dimensional analysis. Again, we'll see that next unit. Let's go on to calculate with this a little bit. This little slide here, and I know you really want me to be showing these videos, but I can't. We just don't have the time, and they're not at the appropriate levels. They're a lot of fun. Go online and look at them. All this is for is to remind you that an intensive property is independent of amount. An extensive needs extra information, i.e. the amount of the substance. So just a good reminder for you. Now, let's take a look at this one. I tried to make them as interesting as possible. It's very ironic, but actually one of my former students got his first job, and he contacted me to tell me he's actually working with hydrofluoric acid. And it's one of these random things that AP Chemistry expects you to know. AP Chemistry expects you to know that HF is going to etch glass, which is made of silicon dioxide. So they know that silicon dioxide is glass, typically doped with other substances to control properties. And the root of where we get that is through sand. And HF etches it or eats away, chemically reacts at it, and it's used in the semiconductor industry. Now, in this case, the question says, how many moles of HF do we have? Hydroic, remember, comes from ide. So we have hydrofluoric acid is HF. I have a volume equal to 25 milliliters, and that's volume of the solution, and it tells me my molarity is equal to 0.588 molar. And so I'm going to plug into the formula. Molarity is moles per liter. Remember, we're talking about the whole solution here. And so 0.588 is equal to moles over, I just have to do a quick unit change here, 0.025 liters. Be careful which direction you go. People have a tendency to sometimes go the wrong direction on that. Now, if we performed that calculation, what we should find is our number of moles is 0.0147, or really to the correct 2 sig figs, it should be 0.015 moles. Don't forget your unit. We get to do a great big shortening of MOLE by just writing MOL. Now let's take a look at another example of this. I typically, didn't this year, but typically ask my students to make solutions for pre-AP chemistry. I use this all the time, every time I have to make solutions for you. So I have a volume in, on your test, you're going to need to learn to save a little bit of time, and listing all your givens in a row like that can take time. So you might want to do it within the context of the problem. That's our volume. I just put volume 1 out of habit. And this is your molarity, and it asks you how many grams. Now, you can do this in 2 steps if you want. The 2-step way would be to first use the molarity formula, solve for moles, and then once you have moles, you use moles to mass, you use the molar mass, and you are more than welcome to do this. I tend to like the single step, 1-step problem. Again, time is a factor in our AP world, so substitute mass over molar mass for our moles and divided by liters. And I'm plug in my givens. I have 0.100 molar is going to equal my unknown mass. That's what I'm after. My molar mass of sodium hydroxide, 1 sodium, 1 oxygen, 1 hydrogen. I'm going to quit prompting you on things like that very soon. That's mass over molar mass. Fortunately, it gave it to me in 2.00 liters. Now, when I solve that, my grams are equal to 7.9994 grams. And I'll tell you what I'm going to do in the lab. I'm not going to round this to sig figs in the lab. I'm going to carry a lab measurement like this. I'm going to carry it to the limits of my balance. So if you're using the pre-AP balances for your lab, which we will do on occasion, they go to that place. We have the 3 nicer ones, and it'll take us to the 3rd decimal place. So you really want to take it out to the limits of your equipment at this point. We're not talking about reporting and misleading people about the ability of our equipment. We want to make the best solution, so we want to carry it out to the best limits of our measuring equipment. Now, in the next video, I'm going to actually lay out how you're going to do that, because we will do that in a lab coming up very, very shortly, and I want you to be a little bit prepared for how we're going to be making these solutions physically in the lab.